All right, welcome back to geometry. We're going to be doing still on Unit 1, Lesson 22. Unit 2 is coming right around the corner, starting tomorrow, I believe. Today, we're going to be talking about the properties of lines and our learning target today. Our learning target today is you should be able to say, I can use geometric axioms or postulates to derive valid inferences. So we're going to talk about what an axiom is or a postulate is in geometry, and then you're going to use these assumptions that we make in geometry, to make inferences. You're going to use that geometry brain, I've been calling it, but it's that logical inference, that logical deduction to uh, deduce, to infer things from premises. All right. Oh, well, let's go to the warm up. So yeah, most of the geometric figures we're going to study in geometry are going to be composed or comprised of straight line segments, triangles, squares, parallelograms, trapezoids, circles. Obviously, those aren't straight line segments, but for a lot of other things, we're going to be using straight line segments. And so we need to talk about some of the axioms or postulates we use in geometry to kind of make inferences about these line segments. And so what we have to know about axioms and postulates, they're just things, they're facts that we take as, we assume or take as being true without being able to prove them or disprove them. Let's take, for instance, make this a little bit clearer. One of the inferences that we make in geometry is that through any 2 points, only one straight line can be drawn. You can draw a curved line between any 2 points, but there's only one straight line that actually fits between any given 2 points, right? So if I was to draw a straight line between A and B, I can draw this line here, right? And assuming this line is directly on A and B, there's no other straight line I can draw that will be on both A and B, right? That's the only straight line that's on both of them. I can do another line segment that's parallel. I can do one the same length. I can do all sorts of things. But there's only one line that will actually go between A and B. Only one straight line. All right? We just kind of have to, this is something that kind of just seems true. It works every time. But it's not something we can prove necessarily. It's something we just kind of assume about things. Another postulate we'll use in geometry is that the shortest distance between any 2 points is comprised of the length of a straight line of a line segment connecting them. So the idea here is that the line that connects A and B here is the shortest possible distance between A and B. And this makes assumptions about space that may not be true physically in terms of Einstein relativity and the warping of space-time, but geometry, the shortest distance between any 2 points is going to be a straight line. All right. All right, so let's do part C here. So 2 different lines will either intersect at 1 point, or they will share no points at all. So let me give you an example, like parallel lines. We're going to talk a lot more about parallel lines. I'm just going to kind of introduce the idea today. So I draw a line, and I draw another line, and assuming I'm going to make these 2 lines parallel. Do you see how these 2 lines are parallel? They don't get closer together or farther apart as far as I go. Think for a second, pause the video, think for a second, are these 2 lines ever going to intersect? If they're parallel, are these 2 lines ever going to intersect? Pause the video, think about it. Hopefully you're unpaused the video now, you gave it some thought, and you thought, I don't think they're ever going to intersect, because if they're parallel, they're not touching, and they're not getting closer, nor farther away from each other, they're never going to intersect. However, we could have lines that maybe could intersect, right? In fact, most lines are not parallel. We could have this one, and then this one. Now, do you see how these two lines, while they are kind of looking like they're pretty close together at first, as we trace them through, this line gets closer and closer and closer until they intersect at one little point over here, and then they start getting further away from each other. So these lines are not parallel. They will intersect at one place. But we only have 2 choices. Either 2 lines are going to be parallel, and they're never going to intersect, or 2 lines on the same plane are not parallel, and they will intersect. And that's an important part too. They have to be on the same plane. We can have lines that are not parallel, that are on different planes that don't intersect, but lines in the same plane, the same piece of paper, right? The same two-dimensional space. If they are not parallel, then they will intersect if they continue on infinitely in both directions, and that's our definition of a line, if you recall. All right, let's go to the next page. Continuing this last part of the warm-up, there is this famous mathematical postulate called Euclid's parallel postulate. And though any point not on a given line, there is exactly one line that can be drawn parallel to a given line. So through any one point not on a given line, there is one and only one line that is exactly parallel to that line. So think about this. Here's a point A. How many parallel lines will go through A and still be parallel to this line here? Well, now I'm going to actually struggle with this a little bit. I'm going to need to use probably a compass to make this work. Yes, I am. That's really the only way I'm going to make this this work out for me here. Nope, I didn't want a protractor. Looking for that compass tool. Ooh, I didn't even know I had that tool. Here it is. All right, here's my protractor. I need to take, in order to draw a parallel line between A and this line here, I need to get my protractor directly on point A. Move point A right there, directly on that point. I'm going to measure. No, that's not what I wanted to do. I need to measure. Take a measurement with my compass so that my compass is directly on the point that I want to go on. And now I can actually make that the arc I want to make. All right, there it is. And now I am going to move my compass once again and keep that same distance over here. And now I'm going to move my line once again. And I'm going to do it one more time, putting my compass right there. I don't need the full circle. I don't need the full circle. Well, I'm giving it to you just to show you. And now I can draw a line that starts here at the top of this circle, goes through. I should probably make this a different picture, a different color. From the top of this circle to the top of that circle. Why does this make a parallel line? Well, this makes a parallel line because I know that the distance between here and here, between A and this line, is going to be the same distance between the line itself and this point here because it's the exact same circle. I took a measurement with my compass, right? And then I put my compass back on this line and I did another circle, which means I know that this distance between here and here is the exact same distance as between A and here. So I have 3 points that are the exact same distance from my original line. So I know this blue line here is going to be exactly parallel to my line here. So we drew one line through A that is exactly parallel through this line. Is there any other line we could draw that will go through A and to be parallel? No, there's really not, right? I could draw another parallel line. I could draw a parallel line from here to here, right? This would also be parallel, this green line here. But it doesn't go through A. I can draw another line through A, a different line through A, but this green line is not going to be parallel with A. So, we have this postulate, this thing we can't prove it's true, it just is. It just seems to work every time, and we don't see a clear way for it to ever not be true, that the only parallel line that I can draw that goes through A and is also parallel with this line is going to be that one line I drew at first, that green line right here. There's no other line I can draw. It will be both parallel and go through point A. Give me that smiley face on the lower right-hand side, that smiley face reflection right here. Give me this reflection and tell me how much that made sense to you. Did you feel comfortable with that explanation? This is kind of abstract stuff. And so I expect some of you are going to struggle with this because once we get into abstract, if it's not concrete, it's hard to imagine. It's hard to think of it, how it applies to real life. So I understand that this can be difficult. Give me that reflection. I'd like to know how many of you are feeling comfortable with what we just talked about, this Euclid's postulate, and which of you were confused by my explanation. Maybe I need to slow it down. Of course, you can always, if you felt that you just need to hear it one more time, it's a video, you can always rewind. All right, let's get on to the exploration, the meat of the lesson. So every axiom we use in geometry can be used in a geometric proof, okay? So it's important that we understand to take them to be self-evident properties that need no proving. We're just going to assume these axioms and postulates we use in geometry we're just going to accept them. They're just going to be true without needing themselves be proved. Every other thing we need to prove using those postulates and axioms and whatever facts we have on the ground. Let's do exercise 2. For each of the following axioms, try to draw a picture to disprove the fact and discuss it if you have somebody with you. Keep in mind that we're talking about straight lines that extend forever in two directions. So through any point on a given line, exactly one point can be drawn perpendicular to the given line. All right, let's break that statement down. Through any point on a given line, so we have to pick this one point A here, point A, that's our given point. Exactly one line can be drawn perpendicular to the given line. All right, so let me draw at least one line which is perpendicular to this point A. And I'm going to need my compass again to do this. All right, I'm going to extend my compass out. And what I'm going to need to do first is put my compass directly on point A, and then I need to draw a circle. And why do I need a circle? Because I need two equidistant points from point A. I need 2 points that are going to be the same distance from point A, and a circle helps me do that. The definition of a circle is all the points that are equidistant from the center. I put my compass on the center, I drew a circle, and now I know all these points are equidistant from A. They're all the same distance. Every radii here is going to be the same distance from A. So then what I can do is I can create a perpendicular bisector. We've learned how to do that once before in class. Here is another demonstration of a perpendicular bisector. First, what I have to do, if you notice what I did there, I expanded my circle a little bit. My compass has to be expanded to a little bit beyond half the distance. So when I draw my next circle, it has to be, my next circle has to be beyond, how do I get this? I'm going to try to get this compass beyond by tilting it. There we go. It needs to be a little bit beyond halfway. So I need to get my compass to do some circle that is more than halfway past A. So I expand my compass so that it's a little bit past A. All right, so there's my circle, expand a little bit beyond A. I don't need the full circle, but I want to show you how to do this. And then I'm going to move my compass over to this side, to that point on my green circle, which I know is equidistant from A. And again, I'm going to keep that compass the same size. I don't want to move the size of my compass. And I'm going to do another orange circle. Again, I don't need the whole thing. I'm just kind of showing it to you because I only really need this part right here. Because this part right here is going to give me my perpendicular bisector. All right, do you see that now, that red line I just drew? The red line I just drew, it goes through this intersection of my orange arcs, and it goes through this intersection of my orange arcs. I have created what is known as a perpendicular bisector. A perpendicular bisector means not only have I cut this in half into 2 equal parts, I kind of already did that by doing the circle. Cutting this piece is now equal to this piece, right? This piece is now equal to this piece because I knew that because all the radii of a circle are equal. However, what I also did was I have a perpendicular bisector. It's perpendicular, which means this is going to be a 90-degree angle. This is going to be a 90-degree angle. I'm waiting for my technology to, oh my gosh, that doesn't work for me. All right, 90 degrees. All right, that's a right angle, perpendicular, 90 degrees. We can make this little square thing here. So this is pretty special. Once you can create perpendicular bisectors, we can like if you wanted to create a 45-degree angle, you could then cut that 90-degree angle in half using an angle bisector that we've learned before. Right? So now that we've done this, we have a perpendicular bisector. I drew the red line. It's a perpendicular bisector. Think about how to disprove it. Can we draw any other perpendicular line that also goes through point A? Is there any other different line we could draw that will do the exact same thing, that will go through A perpendicularly at a 90-degree angle? Like I could draw another line through A. There my blue line there. That's a line through A, but it's not perpendicular. So that doesn't work. I could draw another perpendicular line. Sorry, I'm going to sneeze. Sorry, sneezed. I could draw another perpendicular line perhaps through this. For instance, I'm not going to make it exact or anything, but I feel that like this here looks pretty darn close to 90 degrees. I'm going to assume for the sake of argument here that this is 90 degrees. So I can draw other perpendicular lines through this black line here, but this line, this blue line, does not go through A. Therefore, and I'm going to erase everything, so pause the video here if you need any of this. Therefore, I can conclude that it is not possible to draw more than one perpendicular line that goes through point A. It's not possible. So it is not possible to draw more than one perpendicular line that goes through point A. That's the takeaway here. I can draw one and only one perpendicular line that goes through A. And so the one line that will be perpendicular to this line and it goes through point A. I can draw more than one perpendicular line. I can draw more than one line that goes through A. But there's only one line that is both perpendicular and goes through A. Again, this stuff can get abstract. Give me that smiley face reflection here in the lower right-hand corner. Let me know if this is making sense to you. Again, I do worry sometimes that some of the abstract nature of some of this can be confusing. And if it's confusing, don't worry. We're going to get used to it. We're going to ease you in. But I want to start introducing axiom and postulates at some point. And Unit 1 seems like the point to introduce them. Trying to give you an overview of geometry here. Trying to get you accustomed to all the things in geometry. And we're going to dig more deeply into each piece. All right. Now we have to try to disprove this statement of fact. All right. Through any point not on a line, exactly one. Oh, wait, did I just cut this? Okay. I want to make sure. And through any point not on a given line. Okay, so for any point not on a given line, exactly one line can be drawn perpendicular to the given line. So it says we need to try to think about whether it's possible to draw more than one line that both goes through a point not on the line, and is drawn perpendicular to this line. All right. I'm going to kind of sketch this. I'm not going to, well, no, let's do a little bit better than sketch. Let's bring the protractor out. I could do another perpendicular bisector, but I think for this activity here, the protractor makes a whole lot of sense, because with the protractor, I'm just lining my baseline up here, move it to 90 degrees, right? Moving it to 90, and then I'm just going to place a little mark right here at 90. That's where 90 degrees is, and now my protractor can go away. And now that I got my little purple mark, I can draw my blue line for my purple mark, which goes through A, intersects this line. Okay, this is a 90-degree angle. All right, this is a 90-degree angle. Sorry about that. All right, 90-degree angle. I'm having trouble doing little circles there. For any point not on a given line, that's what we're. So any point not on a given line, exactly one line can be drawn perpendicular to this given line. So can I draw any other perpendicular line? And again, so assume this blue line is infinite, right? It goes in both directions, all the points. That includes all the points between A and this little intersection here. For any point not on a given line, can I draw more than one line perpendicular to it? And again, it's going to be a no. It's going to be a no. I can draw other lines, right? I can draw, let me see here. Let me think about this. I can draw another perpendicular line. Boop. I'm just going to assume for the sake of argument that right there is perpendicular. I can draw this yellow line. It's perpendicular to the line, but it doesn't go through point A. I can draw another line that goes through point A. Looking for a contrasting color. I can draw another line that goes through point A, but this is not perpendicular. That's going to be an acute angle right there, right? So while I can only draw one and only one line that goes through point A and is perpendicular. One and only one line can be drawn between a point not on a line and perpendicular to that line. That's the takeaway. One and only one line can be drawn between a point not on a given line and also perpendicular to that line. Again, give me that reflection. This is abstract stuff. Trying to explain it using these examples here. Hopefully it makes sense. For some of you, this won't be difficult, and this abstract stuff does throw some students for a loop. If it throws you for a loop, don't worry. We're gonna get through this. All right, it's gonna be okay. All right, let's put on our geometer hats for a moment. So I'm gonna cough. Okay, I've mentioned parallelograms earlier in this lesson, but I don't think I've mentioned parallelograms before in this class. So here's your first look at a parallelogram. A parallelogram is a four-sided figure, all right? It has where the opposite sides are going to be parallel, all right? So AB here is parallel to DC, and BC is going to be parallel to AD. That's our definition of a parallelogram. The opposite sides have to be parallel. Let's see. And by inference, we're going to find out that if both sides are parallel, if both opposite sides are parallel, then that means that this side has to be equal in length to this side. So the opposite sides are also going to be equal in length, and which means that opposite angles are also going to be equal in measure. We're going to get into all that later in geometry when we do our quadrilateral unit. The parallelogram ABCD is shown below. Another line is drawn parallel to CD. So if another line is drawn parallel to CD, explain why it must fall on AB. If another line was drawn parallel to CD, parallel to CD passing through A, explain why it must fall on AB. All right. Pause the video for a minute, and I want you to try to envision and just sketch lightly in pencil. I know you guys don't like making mistakes. So lightly in pencil, sketch what you think this is trying to describe to you before I sketch it out. Because this is tricky language, and I want you to use your thinking skills and comprehension here, and see if you can think, what is this telling me? What is this question asking me to do? Pause the video here, see what you can come up with. Light sketch is all I'm asking for. It's okay if it's wrong. If it's wrong, that's not a terrible thing. It means you're learning. All right? It means you're opening up the filing cabinet in your brain, and you're going to be ready to place the right information in there if you don't already have it. Okay? Pause the video. All right. Hopefully you've unpaused the video at this point because you've given this a shot. Okay? Because I even had to read this twice to myself before I'm like, wait a minute, what is this asking? If another line is drawn parallel to CD, so parallel to CD means it can't ever touch CD no matter how long it is. Like AB is already parallel to CD, because that's a definition of a parallelogram. Our definition of parallelogram is a four-sided figure where the opposite sides, where it has two pairs of opposite sides are parallel. So AB is already parallel to BC or CD. If I draw a line parallel to CD, oh no, I didn't do that right. Let me try again. If I draw a line parallel to CD, and if that point also goes through point A, in fact, that one wasn't perfect either, was it, Mr. Sold? All right, I'm talking to myself now, in the third person, no less. Let me try this one more time. I like it to be a little bit more on the money, right there. Now I'm happy with it. Now I'm happy with it. So this yellow line or orange line is going to be parallel to CD, and it goes through point A, and let's notice that this line is right on top of AB, right? So explain, now we have to explain in words, why does it have to fall on AB? Let's try to rephrase what they're asking us. If a line, that's not a good way to spell line. If a line is parallel, I struggle with spelling parallel. I don't know what it is. If a line is parallel to line CD, and if it passes through A, then the line necessarily falls on line AB because line AB contains point A and is parallel to CD. If you want to put this in your own words, by all means. I'm trying to give you an idea of the kind of like exemplar explanation the regents might be asking you for. If they ask you to explain, this is the kind of explanation the regents is looking for. They want you to use very kind of precise language where things are connected to that. You're going to use a lot of if, then, and, or, right? So if a line is parallel to CD, and if it passes through A, then the line necessarily falls on AB because, explanations need a because line AB contains point A and is parallel to CD. So there's a lot of if, thens, ands, ors, thens, then and or goes into these explanations and a because. All right? Because you can put this in your own words if this seems wordy for you. I want you to be comfortable with the language you're using as long as you understand what's going on. We're trying to give you like an exemplar of what is being asked of you, to get that 100 on a Regents or question. All right. So in the following diagram, again, they're letting us know it's not drawn to scale. It's not drawn to scale, which means we can't use our protractor to measure here. We just have to use the description of words they're going to give us in order to make assumptions and inferences. All right. So in the following diagram, which is not drawn to scale, why can't AB and AC be perpendicular to BC? All right. Why can't AC and BC be perpendicular? I'm sorry, AB and AC be perpendicular to BC. Well, you might want to pause the video here and think about this for a moment. What is this question asking you? Think about it. You don't have to pause it. I encourage you to do. Hopefully you took my advice and you started thinking, okay, what's the question asking me? I have to explain why it's not possible. It says can't right here, right? It says can't. I have to explain why it's not possible for both AB and AC to be perpendicular to BC. All right? So why would I explain it? Well, notice how AB and AC are intersecting, right? If I can draw a line like this, and then I could draw another line that's perpendicular to this line, right? I could draw a line that's perpendicular, intersects at a 90-degree angle. I'm going to call that close enough in a 90-degree angle. And then I could draw another line that's like a 90-degree angle. And what do you notice about this purple line and this green line here? What do they kind of share in common? You know, assuming they're both 90 degrees, if you can visualize that. What does the purple line and the green line have in common? Well, don't they look like they're parallel? You see that? How they're both, if I extend this green line further, and I'm going to struggle extending this green line further, aren't I? No, that was pretty close. That's pretty close to extending the green line further. Don't you see how they don't seem to be getting any farther or closer together? They seem to be, that was not quite as good, but it was pretty close. Notice how these are pretty darn parallel. I mean, I just freehanded this. I didn't actually set a protractor to this or do a perpendicular bisector to make sure it's perfect 90 degrees. I just kind of eyeballed it. But assuming that this was that my eyeballing job was was pretty good, two lines that are both perpendicular to the same line are going to themselves going to be parallel. That's another postulate we're going to talk about later. That if two lines are perpendicular to the same line, then the two lines that are perpendicular to the same line are going to be parallel, right? It goes through, this line goes through this point, this line goes to this point, but if they're both perpendicular to the same line, then they're parallel to themselves. So why can't AB and AC both be perpendicular to BC? Because they intersect, because they're not parallel. So let's think, well, I told, sorry about that, I told the PDF to do something I didn't want it to do. I always get tricked by this. And I did it again. Oh, same mistake twice. All right, let me try this one more time. There we go. There's the text box I'm looking for. So, are we ready to explain why it's not possible? Let me start with an if. If AB, line AB and line AC are both perpendicular to the same line BC, then both line AB and line AC would have to be parallel. All right. In the diagram above, line AB and line AC intersect. Therefore, oh, that's another important word we're going to use a lot in geometry. The therefore. If this is true and this is true and this is true, therefore this other thing is true, or this other thing is not true. Again, these are all actually logical operators. Geometry is very much based on logic. It's that very precise thinking. It's thinking in a kind of a precision that's akin to mathematics. You know, actually mathematics is based on logic. In diagram above, line AB and line AC intersect. Therefore, line AB and line AC cannot be parallel. No, I just didn't do it that time. Parallel. There we go. There we go. There's my exemplar explanation. So I explained what would be true, you know, if they were both perpendicular. They would have to be parallel. I said that they intersect. If they intersect, they're not parallel. Definition of parallel means that they don't intersect. Therefore, lines AB and line AC cannot be parallel. Oh, actually, Mr. Salt, but wait a minute. I think I goofed. And I don't think I can undo what I did. Well, let me. Oh, I can. Here, let me fix this. I did do a slight goof, and I would like to fix it. Oh, I can fix it. Good. And again, it's that there's this precision of logic that we have to think. I don't want to say, therefore, line AB and line AC cannot be parallel. They intersect, therefore, they cannot both be perpendicular to line BC. Sorry about that. As I was reading my explanation, I realized that my therefore has to end in why they can't be perpendicular, not why they can't be parallel. So again, there's that tending to precision. I needed to fix that. I'm not trying to prove that they are not parallel exactly. I'm asked to prove why they can't both be perpendicular. So when I say therefore, lines AB cannot both be perpendicular to BC, I've answered the question that was posed to me. Rather than saying it's true that they both can't be parallel. It's true they both can't be parallel if they intersect. That's not the question I'm trying to answer. I got to answer the question I'm given. All right, how is that? Give me that reflection in the lower right-hand corner here. Smiley face for, man, I like geometry. That stuff's easy. Frowny face for, I'm confused. This is a bit much. And something in between where, like, I kind of get it, but gosh, I don't think I can use the fancy terminology you're using. I have to explain that in my own words. That's okay. If that's where you are right now, I'm happy. That's great. We're hitting learning targets. We're using geometric axioms and postulates to derive valid inferences using that geometry mind. I've been talking about that logical brain of ours. Well, I'm going to cough. Okay, and I'm going to pull Euclid's postulate back out, okay, for the check for understanding. I'm going to mostly have you do this. I want to see what you can do with this. Let's pull Euclid's parallel postulate. If you can't remember what it is, let's go back and look. It was right beyond the warm-up. Oh, right, sorry, I went over it. There we go. Euclid's parallel postulate is that through any point not on a given line, there's exactly one and only one line can be drawn parallel to the given line. I can only draw one line that is both goes through A and is parallel to the given line. All right? So back to the check for understanding. Flipping our pages possibly. We have two straight lines that are crossed by another line. When two straight lines are crossed by another line, we call this line here a transversal. A transversal, okay? So two straight lines that are crossed by a transversal will only be parallel if the sum of the two interior angles formed on the same side of the transversal is equivalent to the sum of two right angles. Woo! That's a mouthful. Even I have to think about exactly what's that saying. You might want to pause the video here, read that 2, 3, 4 times until you think you've got it, and make a guess about what you think it's saying. I'm just going to keep going. If you want to pause the video and do that higher level thinking to figure out what is this saying, but I'll explain it now. It's saying that, okay, two straight lines crossed by a transversal. So these are two straight lines, and they're crossed by a transversal. These two lines will only be parallel. They will only be parallel if, there's that if the sum, what the sum? If the sum, that means if I add these two together, if the sum of two interior angles, the two interior angles, these two here are interior angles. These two lines here are only parallel if I add up these two angles and it gives me the same sum as two right angles. What is the sum of two right angles? Pause the video here if you need to think about it. The sum of two right angles. Unpausing the video, a right angle is 90 degrees. Two right angles would be 90 plus 90. 90 plus 90 is 180. So the sum of two right angles is going to be 180. The question is, does 114 and 64 equal 180? Well, let's pull out our handy-dandy calculators, all right? 114 plus 64. I put that in my calculator. You see the answer I get there? 78. Uh-oh, that did not add up. It did not add up to 180. What does that tell me? It tells me these two lines are not exactly parallel. If they were parallel, these two angle measures would add up to two right angles. So let's look at question A here. In the diagram shown, lines M and lines N are crossed by a transversal line. Why is M and N not parallel? Why is M and N not parallel? Can you explain that in your own words based on what I just said? I'll type it in here. If you want to pause it and give it your own go, I encourage that. Actually, you know what? I said it. I do want these check for understandings to be independent. So I'm going to let you put that in your own words. All right? I kind of already explained that. Let's talk about B. On what side, right or left of the transversal, will M and N intersect? On what side, left or right of the transversal, will M and N intersect? So is it going to intersect on this side, on the left, or do you think it's going to intersect on this side, on the right? You take a guess. Can you determine a way to know, based on B, on which side of the transversal two non-parallel lines will intersect? Can you determine a way to know, based on B, which side of a transversal two non-parallel lines are intersect? So, is there any way you could use the angle measures to know which side it's going to intersect? When we add, and I'll remind you, when we added up our angle measures, we got 178, which was 2 degrees less than the 180 we needed to be parallel. So I'll let you answer that. When you're done with the check for understanding, hit me up with this reflection. Tell me what's working. Tell me what you like. Tell me what's going on good with your learning. What needs to be improved in the classroom. Let me know here. The comment sections of a YouTube video, right? Give me your comments. Subscribe, right? All right, homework time. Geometry is full of patterns, and the very first axiom about straight lines we assume is that through any 2 points, there can only be one straight line drawn, right? Between any 2 given points, there's only one line that can be drawn. What if we have 3 points? Whoops, 3 points. What if we have 4 points, 11 points? Assuming you have 3 non-collinear points, how many unique straight lines can you draw? All right. I like this. This is kind of like fun. This is like, okay, let me delete all the stuff I've gotten from before. I can draw this straight line, 1. I can draw this straight line, 2. I can draw this straight line, 3. Are there any other straight lines I can draw? I don't think so. So with 3 non-collinear points, I can draw 3 lines. So that's what you could write here. I can draw 3 straight lines. What about if there's 4? All right, if there's 4 non-collinear points, I can draw 1 line. I can draw a second line. I can draw a third line. I can draw a fourth line. Am I done? Am I done? Does anyone think I'm done? Hopefully not, because I'm not done, right? I can draw a fifth line. I can draw a sixth line. I can draw 6 lines through 4 collinear points. Isn't that something, huh? All right. There's a pattern we can use to exploit and predict how many straight lines can be drawn through any number of points. Let's think about that pattern here. If we have 2 points, only 1 straight line can be drawn. If we have 3 points, then 3. Whoop. Nope, sorry. I have to get better at this technology. Oh. Sometimes technology doesn't like to play well with different parts of the other technology. All right, I can draw 3, right? But 4, I can draw 6. All right, are we starting to see a pattern here yet? Let's talk about this one. Let's see. What do you think? If we had, if we had 5, if we have 5 points, what do you conjecture will be the next amount of lines, huh? Let's think. Let's see, there's going to be 1, 2, 3, 4, 5, 7, 8, 9. See what's going on now? 10, 10. I think I'm done with 10, right? I've got 1, 2, 3, 4, 5. Ooh, lightning. 6, 7, 8, 9, 10. Oh, I have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've got 11 here. All right. Very good. That's what I got for you today. You've hopefully hit that learning target that you're using geometric axioms and postulates to derive some valid inferences. That's what we got. Have a great day. Remember, we matter.